In this video lecture, we're going to solve the particle in a one-dimensional box, the Schrodinger equation for that system. And what we'll find here is the solution is these are the wave functions and these are the energies, and that's how you solve the Schrodinger equation for a particle in a 1D box. Let's first start with the Schrodinger equation, and we'll see how we get that solution. H psi equal E psi. That's the Schrodinger equation. We want total energy, so we want the total energy operator. As we said classically, the total energy was just a kinetic energy. We transformed that into an operator. So the operator minus h bar squared over 2m times the second derivative with respect to x squared. That's the operator for kinetic energy, and that's the only system, or the only energy we'll have, because in the particle in the box the potential we set equal to 0, and it's a constant, doesn't vary with x. So now we can write the Schrodinger equation as minus h bar squared over 2m times the second derivative of the wave function with respect to x. That's equal to e times psi, where psi here is a function of x. Let's rewrite this equation to get into a form that maybe is more familiar to us. Let's multiply both sides of this equation by minus 2m over h bar squared. This will give the second derivative of the wave function with respect to x here. That's equal to minus 2 times the mass times the energy over h bar squared times the wave function. This you might recognize as a linear, homogeneous, ordinary differential equation, and we've considered those in general, so we can immediately write down what the solution is here. Here, psi, as a function of x, will just be equal to a1 e to the I kx plus a2 e to the minus I kx, where k, remember this was k squared, so k is equal to the square root of 2me over h bar squared. Okay, so that's what the solution is, and we've now solved it. However, in most introductory physical chemistry textbooks, the solution is not given in terms of this. It's given in terms of sines and cosines. So let's make that transformation. We'll use the Euler relation e to the I kx. That is equal to cosine of kx plus I sine of kx. That's the Euler relation. So let's express these exponents in terms of sines and cosines. So psi of x, all right, we're going to express this as that, so that would be equal to a1 cosine kx plus I sine kx. All right, and then this term, in terms of the Euler relations, will be a2 times cosine kx minus, this is minus I, put a minus I there, that becomes minus, minus I sine kx. All right, let's group terms that have cosine and sine in them. So we'll have psi of x. That will be equal to a1 plus a2 cosine kx plus I times a1 minus a2 sine kx. Let's give these a different name. We'll call this a C1, and this, including the I, call this C2. So we can write the solution to the Schrodinger equation, the wave function for the Schrodinger equation for a 1D particle in a 1D box, as C1 cosine kx plus C2 sine kx. Now, so far we don't know what C1, C2, K, or K is. Well, we do know what K is in terms of the energy, but are there any restrictions on K or anything like that? It looks something like this. where we're plotting on the y-axis here the potential as a function of x. This goes up to infinity. This goes up to infinity. X-axis goes from 0 to a. And so the particle is constrained to be in this region in x, and it does not have infinite energy, so it can't go up, and it's not over here. All right, so what does that mean? Can we put any constraints on the wave function? Well, let's look over here when x is equal to 0. We know outside the box, right outside the box here, the wave function has to be 0 because the particle is not there. It has to be constrained inside the box. So just outside the box, the wave function has to be 0. And because the wave function has to be continuous, that means just right inside the box, the wave function has to equal 0. So with those considerations, we know that the wave function at x equals 0 has to equal 0. Let's look here. If you put in 0, the cosine of 0 is 1, and here sine of 0 is 0. So this means you cannot have any cosine character in the solution, because if it is, then this boundary condition is not met. So this implies that C1 is equal to 0. You got to get rid of that cosine because it doesn't meet that boundary condition. So now you have the wave function psi of x is equal to C2 sine of kx. Now let's look over here on the other side of the box. By a reason similar to what we used over here, the wave function at this side of the box has to be 0, because right outside that is the wave function is 0, and the wave function has to be continuous. So this means that the wave function where x is equal to a, that has to equal 0, and when x equal a, the wave function now is c2 times the sine of ka. All right, well, what does this mean? This means that k cannot be any number. K has to be a number that will set this equal to 0. Now you're saying, well, what about C2? Can't C2 be 0? Well, sure, but if you put C2 0, the wave function is 0, and so there's 0 probability of finding the particle anywhere in space, so it doesn't exist. So C2 can't be 0 if you want to have a particle. So this means sine kx has to be 0, or sine ka has to be 0. Now, if the sine function is 0 when this term is 0, so you could say that ka, because of this boundary condition, can be 0. How about what's the next value? Well, pi, be pi. How about 2 pi, and so on. So a compact way of writing that is ka has to equal n pi, where n is equal to 0, 1, 2, and so on. All these values of n will make the sine function 0 and satisfy the boundary condition on the right-hand side. Okay, well, let's look at this a little more closely now. Let's go down to a new page. So now our wave function, psi, and we're now going to characterize it by a quantum number n. So we'll get a different wave function for different values of n is equal to c times sine of k x, where k is equal to n pi and ka, sorry, n pi, where n is equal to 0, 1, 2, and so on. Let's look a little more closely where n is equal to 0. If n is equal to 0, then that means the sine is 0. C is it is independent of x, so that means the wave function is 0 all the way across the box. So we want the particle to exist. We want it to have some value of the wave function not equal to 0. So by those arguments, you can get rid of the n equals 0. So really, n equal 1, 2, and so on up to infinity. So note now we've introduced a quantization. N can't be any number. It has to be an integer. So here this n is now our first quantum number. Quantum number. And the quantum number came about because we required the wave function to be 0 at the boundaries, here and here. Okay, so it's a quantum number. So we say, all right, fine. That's what that is. Now K, A is equal to n pi, or K is equal to n pi over A, where n now starts from 1 and goes on up. And remember also, by the Schrodinger equation, we said that K is also equal to, because the solution of this equation, now square root of that was K, is 2me over h bar squared square root. All right. So that's equal to 2me over h bar squared square root. So let's solve this for E. E is equal to n squared pi squared h bar squared over 2m a squared, where n now is equal to 1, 2, and so on. So now we have quantization of energy levels, because n can only be 1, 2, or 3. It can't be 1.5 or 3.4 or anything. It only has to be those. So if we go all the way back up here, because we want the wave function, we're constraining the wave function to fit those boundary conditions. We get only certain wavelengths, only certain wave functions, and only certain values of n. So now we have quantization. All right, so let's check back here. Okay, so yes, we understand where this comes from, E sub n. We're almost here. If we contrast and compare our wave function here, let's substitute in what k is. This is equal to c times sine. K is equal to n pi a over a, so this is n pi x over a. Contrast that. Yeah, sine n pi x over a. But where did this thing come from? So we're almost there. C is an undetermined, or that's an undetermined as yet, undetermined constant. How do we define what C is? Find what C is. Well, here we use a normalization condition. So we want, if indeed the wave function is a probability density, if we integrate from minus infinity to plus infinity of the square of the wave function, and we're taking square because generally wave functions can be complex numbers, so we have the complex conjugate times that. That'll give you a real number. Integrate over all space, that has to equal 1. So let's apply this normalization condition to the wave function we just determined for particle in a 1D box. So we have the integral from minus infinity to infinity of c sine of n pi x over a complex conjugate times c sine of n pi x over a integrated over dx. All right, now there's no I term in here, so the complex conjugate is the same as this, so we no need to change I to minus I, and we want this to equal 1. C is a constant, so we can pull that outside the integral. This becomes c squared, integral from minus infinity to infinity, of sine squared n pi x over a integrated over dx. Okay, and note that the integration goes from minus infinity to plus infinity. However, if you look at here, okay, we can change those integration limits from minus infinity to plus infinity to 0 to a, because the wave function outside the box is 0. So if you just integrate there, you're going to get 0. So why not start the integration at 0? Same way with a greater than 0, with x greater than a. So we can change the limits of integration without losing anything. It's just c squared, the integral from 0 to a of sine squared n pi x over a integrated over x. Now back in the old days, you had to look up this integral in a table of integrals in a book, or do it yourself, integration by parts perhaps, or something like that. But nowadays we live in the age of the internet, and we can just go to a site called Wolfram Alpha, wolframalpha.com, and you probably heard of this before. They probably use this in calculus nowadays. And so what we want to do is we want to integrate from 0 to a of sine squared n pi x over a dx, where n now is an integer. Remember, n goes from 1, 2, 3. So let's, I've already typed this in here. Let's see if we can make Wolfram alpha understand that. Integrate from 0 to a sine squared n pi x over a, where n is an integer. Okay, Wolfram alpha, let's see how smart you are. Well, not too smart here. Closest Wolfram interpretation, what, 2 n pi, we don't want to integrate that. What's it talking about? Well, it turns out it's not smart enough to recognize the phrase when n is where n is an integer. So, all right, not quite there yet, not quite total good artificial intelligence. So let's get rid of that, where n is an integer. And let's see if it can understand what you want to do without that. Okay. All right, looks like it understood that. So here's the integral we want, 0 to a sine squared n pi x over a. All right, that's 1/4 a times 2 minus this quantity. Well, let's use the fact that n is an integer. It's 1, 2, 3, and so on. Suppose n is 1. Sine of 2 pi is 0. Suppose n is 2. Sine of 4 pi, 0. So as long as n is an integer, that means that this term will be 0. So the definite integral is a over 2. Okay, well, that's handy to have that. So this integral here is equal to a over 2. So we can write this as c squared times a over 2, and we want this to be equal to 1. This implies that c, that integration constant, or the not the integration, normalization constant, is equal to the square root of 2 over a. All right, so we know what c is, and finally we can write the wave function now, characterized by quantum number n, is equal to the square root of 2 over a sine of n pi x over a. All right, so we've gotten here. Okay, so that's where that square root of 2 over a comes from. It comes from the normalization constant. We want these, when we multiply them together, when we square them, we want it to be equal to 1. Now, another useful property or useful thing to have for wave functions is that they're orthogonal, meaning if you take one wave function and multiply it by another and integrate over all space, you'll get 0. So let's see if that's the case for these wave functions. In other words, if we have another wave function, say psi m, characterized by its quantum number, square root of 2 over a sine of m pi x over a. If these are orthogonal, that means that if we take, say, psi m, complex conjugate, times psi n, this is how you square a complex number and get a real number. We want to integrate this from minus infinity to infinity. We want this to equal 0 if m and n are different. Okay, well, let's apply that here. So we want the integral, again, for similar reasons we used for the normalization integration, we only need to integrate from 0 to a. So this would be the integral from 0 to a of psi m star. I was going to write what psi m is, so let me do that. Psi m is the square root of 2 over a times the sine of m pi x over a. And we're going to take the complex conjugate, although there's no I in here, so we don't need to worry about that, times the square root of 2 over a sine of n pi x over a. And we're going to integrate this over dx. Okay, Wolfram alpha to the rescue. All right, we'll put in here what we want to integrate. You want to integrate from 0 to a of sine of m pi x over a times sine of n pi x over a. Okay, Wolfram alpha, show us what you got. Okay, here it is. This is the integral. Yeah, that's what we want to integrate. We're just checking. So here it is. Sine, cosine, cosine, sine. Now remember, m and n are integers. It's something we couldn't tell Wolfram alpha, but we know it. So m and n are integers. So let's say m is an integer. Well, sine of an integer times pi, if the integer, say, is 1, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0. So since m is an integer, this term goes to 0. Same way here, if n is an integer, this term goes to 0. Now, if, sine of pi, sine of 2 pi, and so on, so this term is 0, that term is 0. So what this means is that this integral is 0. So indeed, this is equal to 0. So if you take these two wave functions with different n and m, you integrate, multiply them and integrate over all space, you get 0. So m and n are orthogonal, or different. This implies psi m, psi n are orthogonal. Okay, now here's a subtlety. Suppose m and n are equal. This means that this term down here will be 0. If that goes to 0, this term blows up to infinity. So what we have to say here is that m is not equal to n. And that's okay because we're saying n and m are different wave functions. All right, now let's see what these wave functions look like. Let's plot these as a function of, say, n. What I've done is I created an Excel spreadsheet which plots the wave function and the probability density, the wave function squared, as a function of distance for various values of n. Here's the edge of the one-dimensional box. The wave function has to be 0 there, and here it has to be 0 there. That's our boundary conditions. And because of those boundary conditions, we got quantization of energy levels and of the wave function. All right, so right now n is equal to 1. This is what the n equal 1 wave function looks like, and if you square that, this is the probability density. Let's see what n equal 2 is. N equal 2, here's the wave function. It goes up and then goes down and goes up. This is higher energy. It's higher energy because you have more curvature in the wave function. If we square this, we get something like this. There's the node. The node is where the wave function goes from positive to negative. And there's 0 probability of finding the particle right there inside the box. Here x goes from 0 to, what's it going to? 10. So here a is equal to 10 in some units. Okay, let's look n equal 3. And I'll post this on the Blackboard site so you can play around with it if you want. Here's n equal 3, starts at 0, it has to start at 0, goes up 1 node, 2 nodes, and goes back down. If we square that, here's the probability density, 2 places where the probability is 0, absolutely sure you're not going to find the particle there. And let's say n equal 4. All right, here's the 4, n equal 4, and so on. Let's put a big number, say n equal 50. There it is. So here it goes up and down. There'll be 49 nodes, and here the probability distribution is looking more constant and so on. Let's go back down to 1. All right, the probability distribution here is most likely to be in the center of the box and not likely at all, in fact 0 right at the edges of the box. All right, well, classically, what does this mean? Classically, you expect that there be equal probability going all the way across the box. The potential is constant is equal to 0, so the particle will be anywhere in this box equally probable. Yet quantum mechanics says for the n equal 1 state, it's not equally probable. In fact, it's 0 at the edge, and as you go up, it's most probable here and right at the middle of the box, and it goes back down again. Let's look at the n equal 2 state. All right, again, it's most probable on either here 25 or 75, or in this case 2.5 or 7.5, and there's 0 probability there. Again, not what you expect classically. Classically, you'd have just constant probability all the way over there. Well, let's now look at 50. Now, as you get increasing the number of nodes, or increasing the quantum number, pretty soon you're starting to get a flat distribution across the box. And as n approaches infinity, what you'll find is the probability distribution will be flat across the box, and it'll be so many, and as n goes to infinity, you'll have an infinitesimal separation between these individual probability peaks. You won't be able to measure it by any measuring device because you can't measure infinitesimal changes by any measuring device, so it'll appear as if the probability is constant across there. So if we have probability, or for the n equal 1, it's not constant, but as you increase the quantum number, then the probability becomes what you would measure classically, and that's the example of the correspondence principle. The correspondence principle says that what you measure quantum mechanically has to approach what you measure classically for large numbers, large values of the quantum number. Okay, so that pretty much does it for the 1D, the solutions to the quantum mechanical problem of particle in a 1D box. Well, there's the solutions, the wave functions and the energies. Well, I suppose we should talk just a little bit about energies before we go here. So we say that the energy, characterized by some quantum number n, is n squared pi squared h bar squared over 2ma squared, where a is the length of the box, and n is equal to 1, 2, 3, and so on. All right, well, let's see. N equal 1, here's that energy level. The energy level is pi squared h bar squared over 2ma squared. That's that energy when n is equal to 1. When n is equal to 2, the energy is 4 times this quantity. When n equals 3, the energy is 9 times that quantity, and so on. So the energy levels are not evenly spaced. In fact, the spacing between them increases as you increase a quantum number. 1, 4, 9, 16, and so on. So the difference here is 3, difference here is 5, difference there is 7, and so on. Okay, so those are the energy levels, what they look like for a particle in a 1D box. So that's it, I think. Yes, I think we've discussed all there is to discuss about particle in a 1D box.